In section 11.3, the title shouldn't just be quarks. It should be quarks and gluons, because we're going to take a look inside the nucleons, the proton and the neutron. We're also going to look at even more exotic particles that contain quarks and are bound together by gluons. Now, this is a very complicated interaction that the quarks and gluons have, and we refer to the theory about this interaction as QCD, quantum chromodynamics. So there's going to be a lot of things at play here. There's going to be something we call a color charge, which is responsible for holding it all together. And then there is going to be this idea that the force actually gets stronger as you pull the particles apart. In fact, the gluons, which are basically the particles responsible for holding everything together, actually stick to themselves. So I suppose the term gluon is very, very appropriate. So let's get into it. Looking at quarks, basically we know that there are 6 different quarks. They were originally discovered in the 1960s. Originally, 3 of them, the 3 lightest quarks, were discovered first. And that doesn't really surprise us, because when we think about the discovery of particles, we're really at the mercy of how powerful the machines are that we use to create these particles. Lighter particles tend to be more stable. Heavier particles tend to be less stable, decay more quickly. But heavier particles by E equals mc squared, Einstein's famous equation that we get from relativity, states that you need more energy the more mass that you wish to create. So again, up, down, these are the 2 quarks that are very common in our universe right now. They are the subparticles of the neutrons and the proton. And then the heavier quarks, the next level, is charm and strange. And then after that, we have the top and bottom quark. Now, again, these were first proposed in 1963 by Murray Gell-Mann and George Zweig. And going back to the symmetries that we talked about in the previous section, this threefold symmetry led them to propose the existence of 3 quarks, which were soon discovered in particle accelerators. And really, the first 3 quarks, the up, down, and strange quark, were discovered in the Stanford Linear Accelerator. And the way we can understand how we discovered them is, think back to the Heisenberg uncertainty principle. Actually, think back to de Broglie's wavelength. As we have more and more energy in these particles, their wavelength is getting smaller and smaller. So when we first discovered the nucleus, we were using fairly unenergetic particles as they go, and we were bouncing off of them, and we saw, oh, there's a big mass at the center. When we began to probe the nucleus and resolve the individual of neutrons and protons, we needed more energy, because what we were just simply doing is the particles that we were, quote, seeing with had to be a smaller wavelength, on the order of protons and neutrons. To see even greater detail, you have to hit things with higher and higher energies. So this is a recurring theme. In many ways, our particle accelerators act like microscopes. And if we want to see finer and finer detail, we have to go to higher and higher energies. Of course, there are consequences that result from that. We can't interact with something without something happening. So for instance, the harder we hit these particles with these more energetic, probing, whatever we're going to use, an electron. Stanford Linear Accelerator actually was using electrons to probe within this. The greater the chances that we're going to actually create new particles. And the bottom quark, which is the lightest of that 3rd tier of quarks, was discovered at Fermilab using a more powerful accelerator in 1977. And then finally, the top quark wasn't discovered until 1995 when they were able to, achieve the very, very high energies that was associated with the top quark. So again, it's interesting. We saw that threefold symmetry in the previous section, and then that led to the idea, well, there must be three underlying particles responsible for that. But the story didn't end there. If we go to even higher energies, we come across the other particles. Now, quarks are strange. Quarks cannot be free, okay? You're probably aware that quarks have partial charge. We've brought that up before. The down quark has a negative 1/3 charge. The up quark has a positive 2/3 charge. But when we learn about, electricity and magnetism, when we learn about the elementary charge, we know it's 1.6 times 10 to the minus 19 coulombs. It's not, 1/3 of that value or 2/3 of that value. And the reason we don't see these partial charges in nature is because they don't exist freely in nature. Now, when the universe was very old, I'm sorry, I guess it was very old, when the universe was very young. When the universe was very young and it was hot, the temperatures were such that the temperatures and densities were such that all these particles were pushed together in very tight spaces, if you will. And this allowed the quarks to actually be free, what we call a quark gluon plasma. And that really was the last time that we saw these particles by themselves. But, it's almost akin to a plasma. If you let a plasma cool off, all the electrons are grabbed on to by the positive ions, and you sort of have the atoms condense into molecules, if that's at all possible. And you no longer have free particles. You can think of the evolution of our universe as sort of having the same thing, that the quarks were free at a higher energy and density. But as things cooled off, they condensed into these individual particles, just like I was driving in today, and all the water molecules were condensing into fog particles, and it was making it more difficult to see. Here, this is akin to this sort of the same process. As we go to lower energy, particles tend to condense, and that's what we have here. So what do they condense into? Well, they can condense into mesons. Basically, quarks can pair up with an antiquark, producing a meson. Here's what's known as the pi meson. This is a pi plus meson, and that is an up quark and an anti-down quark. These mesons are very important for holding the nucleus together because protons and neutrons will exchange virtual versions of these particles to create an attractive force. So that is one way that quarks can be held together. But because you have matter and antimatter, these mesons are typically pretty short-lived. Hadrons, however, some of them are very unstable because they're composed of massive quarks, but the neutron and the proton are pretty stable, okay? It's not well known, I should say it's not known if the proton decays, over a very, very long half-life. You don't even know what it would decay into. But the neutron, we do know, decays into a proton via the weak force. But the heavier and heavier hadrons will decay into lighter hadrons, and usually the result is we produce protons and neutrons. So hadrons are typically three protons that are grouped together, three quarks that are grouped together, and we'll explain why three. Why do we have three? It's very much aligned with the idea that unlike the electric charge, which can be positive or negative, there's two charges, we're going to have three color charges. So we're always going to see the hadrons grouped together in threes. So 6 quarks. There's an up quark, a down quark, a charm quark, a strange quark, a top quark, and a bottom quark. And we can see that all of these quarks are fermions, meaning that they have spin 1/2 or some integer times 1/2. And if we look at the charge, the up quark and its antiparticle have plus 2/3 of an elementary charge, or minus 2/3 respectively. Their baryon number is 1/3 or negative 1/3. We talked about the baryon number as being conserved in most interactions. And we can see that the up quark is the lightest of all the quarks. Now, this is an important point. What's surprising about the proton and the neutron is they weigh so much more than the three quarks that make them up. And that is an important point that shows us that these nucleons are not just the three valence quarks. They are also, as we'll see, a sea of virtual particles, and they're also a sea of gluons, which hold the whole thing together. As we go from the up quark to the down quark, the neutron has more down quarks than up quarks. Proton has 2 up quarks, 1 down quark. We see the mass gets a little bit heavier, and this is why the neutron can decay into the proton. Then we get to the charm quark, and there's a huge jump. In fact, the strange quark was discovered first. It is an order of a magnitude lighter. Not surprisingly, it would be discovered first. And it is sort of a second tier. I'll use terms that aren't usually used, but it's sort of the second generation version of the down quark. So here we sort of reverse things. You know, the strange quark is actually lighter than the charm quark, or the down quark is heavier than the up quark. So the charm quark is that second generation to the up quark. And then we take a huge jump, the bottom quark and the top quark. We're going from 1 order of magnitude to not quite an order of magnitude jump, but certainly a huge jump as we get to the top quark's mass. And those are the 6 quarks that we know of. Do we suspect that there are any more quarks than that? At this point, we don't have any reason to believe that there's a 4th generation or a 5th generation. But they would exist at, you know, incredibly high energies. And again, I can't, you know, even suspect whether or not, you know, such a more energetic quark would be possible. I've never read that anybody has provided any evidence, theoretical or experimental, that anything else exists. But here's interest. This is an interesting chart because it shows us on a log scale. So again, every time we're jumping this amount here, we're increasing by 1 magnitude. Here's the up quark, here's the down quark. Big jump to the strange quark, big jump to the charm quark, you know, big jump to the bottom quark, and then a sizable jump to the top quark. So we can see where, you know, the up and down quark are the quarks that these other quarks can decay to via the weak force. You know, all systems like to go to their ground state. Again, when the universe was very, very young, we're talking about, you know, fractions of seconds very early on. The top and bottom quark were very common, but as the universe cooled off, everything likes to go to lower energy states. So decay took place to the 2nd generation, and finally the 1st generation is pretty much what we find most commonly today. You know, think about what's around today in terms of, you know, what normal matter is made out of. It's made out of atoms, right? You know, we don't know what dark matter is made out of, and we don't know what dark energy is made out of. But of the normal matter that we know of, it's pretty much boring stuff. Up quarks, down quarks, okay, making protons and neutrons, and leptons such as the electron, okay? Once in a while, we create a muon. Once in a while, we create a particle with a charm quark, strange quark. But for the most part, these other quarks, we really don't see today. So we use our time machine, our particle accelerators, to turn the energy of these collisions into mass and, you know, create these particles of a long time ago. So again, quarks are held together by the strong force. I'm using a diagram that I created that probably isn't, very accurate, but we can understand these quarks being held together by gluons. In the nucleus, the term valence quark is used to say that these quarks exist as real particles as opposed to virtual particles. But when we look at things in terms of particle field theory, okay, the on a smaller and smaller scale, these particles are not hard spheres like we demonstrate them to be right here. These are excitations in different particle fields, and basically we would say that these quarks are promoted to a high enough level, just like if we have an electron, a valence electron, they're promoted to a high enough level that they're not constantly popping in and out of existence, but they're surrounded by this sea of virtual excitations, okay, which we represent as particles, virtual excitations of both quark-antiquark pairs and gluons, which are going to hold the whole thing together. So here is a whole list of different baryons. These are, in fact, well, they're not only just baryons, they're hadrons. And we can see our proton up, up, down, neutron up, down, down. And again, interesting thing happening here, very much like you can get an excited atom where, normally we fill up the shells, spin up, spin down, spin up, spin down. We do the same thing with the quarks. There are energies within these particles themselves, protons and neutrons. So I can actually go from a proton, theoretically, to a delta plus particle simply by taking one of the up quarks and flipping its spin so it's up. So our up quark is spin up, spin down, up quark, spin down, up. So 2 1/2s up and 1 spin half down gives me a total of 1/2 spin. But if I put them all spin up, I'll get this particle right here. So this is sort of an excited version of the configuration that we have for the proton. Likewise, delta plus is the excited, I'm sorry, likewise, delta naught is a excited version of the neutron. So, don't think that it's just what quarks are present, what valence quarks are present, that determines the type of baryon that we have. It's also what energy and spin that they have within here. And you can see here we can have an up, up, up quark, up, up, up configuration, producing a delta plus plus that has an elementary charge of +2. And here we have a down, down, down. That's a delta minus. Each of the down quarks has a charge of -1/3, so we add them all together. And then we get into the strange quarks, okay? Here's an up-down strange, spin 1/2, okay? This is like a really heavy neutron, if you will, the lambda 0 or the lambda naught particle, where instead of having that down quark is a heavier strange quark. And here's like a heavier version of a proton. This is a charmed lambda plus. Again, spin 1/2, just like the proton, but it's a lot heavier. It's got an up, down, and charm. The charm replaces that up quark. And we were seeing so many of these exotic particles just being created by slamming particles together in these particle machines, these particle factories, which are particle accelerators. And particle physicists were just looking at the results and going, wow, there's a new particle, there's a new particle. There's this whole sea of particles And Gell-Mann and Zweig said, well, we can simplify this thing, just like you can have different configurations of protons and neutrons in the nucleus to produce different elements. We can go on a smaller scale and have different configurations of more elementary particles, the quarks, to create this zoo of particles that we see being created. So, that was quite a revelation, which led to the discovery of the quarks. And sure enough, we start slamming electrons together at very, very high energies, and we start seeing the emergence of these quarks themselves. Here are mesons. Remember, mesons are a quark-antiquark pair. I've listed hadrons here, which are all made out of quarks. If we have them made out of antiquarks, they would be anti-hadrons or anti-baryons. Certainly, the antiproton would be an anti-up, anti-up, anti-down. The anti-neutron would be an anti-up, anti-down, anti-down. And any of these particles, even the omega minus particle, would be three anti-charm quarks together. So here we have the mesons, and I can't pretend to completely be able to understand these linear combinations, but in some cases, if we, again, don't try to think of the quarks so much as hard particles, rather than their excitations, it's easier to accept that, for instance, some of these particles, like the neutral pion, is a linear combination of an up and an anti-up and a down and an anti-down. So is the case with a neutral rho, but of course, there, instead of having spin up, spin down, you're doing two spin ups. So really, you think about these excitations as waves in these particle fields. It's a little bit easier to understand how we can have a linear combination of particles, like how do we have an up and an anti-up at the same time as we have a down and an anti-down, and not have four particles in there? Okay, linear combination of these waves superimposing themselves on one another. And again, I hope I'm doing justice to that explanation. Here we actually have would I consider that? Yeah, four pairs of anti-particle, anti-quark, anti-quark pairs put together. How can you have a negative? Again, we're dealing with waves here. It's really, phase relationship between the two. So quarks are bound together by exchanging these virtual particles we call gluons. And gluons are akin to what the photon is, the electromagnetic force. So for instance, if we want an attraction force between a proton and an electron, okay, they will exchange virtual photons. Photons are, of course, the particle for the electromagnetic force. So if I have an electron coming near another electron, they will repel each other by exchanging virtual photons. Photons are the virtual particle, the boson, the field boson for the electromagnetic force. So with the gluon, we have the same thing going on here, but there are important differences between the gluon and the photon. Well, first of all, with the gluon, they actually carry the charge with them. So for instance, when we're looking at the photons, they're not positively or negatively charged. They have a field, an electric field and a magnetic field, but they have no charge. The gluons actually carry with them the color charge of the strong force. So each of the quarks have their own color, as we'll see, and the gluons will carry the color charge with them. The other thing that is interesting is they have mass. So they, you know, they're going to be limited in their range, much like the W, the Z particles were limited in their range with the weak force. Okay, so free valence quarks bound together by these gluons. This is what we'd see if we start scattering particles off the protons and the neutrons at lower energies than we're going to look at next. Okay, if these are still very high energies that we need to actually bounce particles off and see these valence electrons. Remember, it was done in the 1970s with the Stanford Linear Accelerator, and it's very much akin to Rutherford's gold foil experiment, where he bounced alpha particles to discover the nucleus. But if I use higher energy particles, I can actually see the individual quarks because I'm going to smaller and smaller wavelengths with higher energy probing particles, and the wavelengths will be on the wavelength of these quarks. So if I use too large of a wavelength, the particles that come in will just see the neutron, or they'll just see the proton. I've got to get the wavelength small enough that I can, strike individual particles and get a reaction from that. If I go to higher energies, what do I start seeing? Well, now I start seeing these quark-anti-quark pairs popping up. Where are they coming from? Well, remember, these valence quarks are actually surrounded by these oscillations in the particle field, in the quark particle field. Okay? And there's an up quark particle field, a down quark particle field. There's particle fields for all of these, but they're all oscillating around these valence quarks. And if I hit them hard enough, I can actually promote them with enough energy to become real particles. Remember, virtual particles are borrowing energy. One way of thinking about it is because these are all models that we use to try to create ideas which are from the macroscopic world that we're comfortable with and apply them to a microscopic world to, try to at least get some understanding or be able to predict what's happening. But, again, we can think about these high energy particles coming in with even smaller wavelengths and interacting with these virtual particles to get an interaction. Go to higher energies, and we see even more detail. We see a really fuzzy, ball of particles popping in and out. So our original view of the protons and the neutrons as being, just three quarks stuck together is really not fair, because yes, maybe we can say these three virtual particles, these three valence quarks dominate the proton and the neutron. But if you go and you add up the mass of the up quarks and the down quarks and the protons and neutrons, you don't even get close to the value for the mass of a proton and a neutron. You need the interaction of all these other particles going on to give these particles their true properties. And, the valence particles are responsible for the spin. Spin up, spin down, spin up gives us a 1/2 spin for the neutron, and spin up, spin down, spin up gives us the 1/2 spin for the proton. But all these other particles do contribute to, holding this together, but also the mass, E equals mc squared, the energies associated with these virtual oscillations, in these particle fields, are responsible for what's going on here. So, and I stole this picture, so I want to give credit to the person who put it together, you know, these pictures I can draw myself, but this is a really a beautiful picture of a representation. We can't actually see, what inside a proton or a neutron, but we use these diagrams to represent what's going on in here. Here you see the three valence quarks, beautiful representation. They're fuzzy, they're oscillating. And then you see a lot of these other particles around it, these virtual quarks popping in and out of existence. And then this grayness behind that, those are the gluons that hold it together. And by the way, these little springs, that's usually the representation that we give for the gluons. If you saw them in a Feynman diagram, it'd usually be represented by this little spring type symbol, whereas things like photons are often represented by little oscillating waves. So that's why we use springs. And yes, if you could actually visualize the gluon, it wouldn't be a spring. Now let's talk about the color charge, because what holds the electron to the nucleus is the electric force. Opposite charges. We've got a negative charge in the electron, we have a positive charge in the nucleus, and that's what's going to keep the electron sticking around. The electric force is not what holds the nucleons together. It's not what holds the protons and neutrons together. If it were up to the electric charge, the proton would fly apart. Okay, the two up quarks have a plus 2/3 charge, and even though the down quark is a negative 1/3 charge, the net charge would tear it apart. So we have color charge. It has nothing to do with real color, but because it came in three, we know the human vision is based on three primary colors. They said, oh, okay, let's just take the three additive primary colors. In light, there's three additive colors and three subtractive colors. So that red, green, and blue is a color charge that they're given. And this is basically the charge that was assigned to the strong force. And it just was very convenient, because if you take red, green, and blue and you add them together, you get all colors, or you get white, which they sort of say is neutral. Of course, if they used the subtractive colors, that might have made more sense. Magenta, cyan, and yellow. If you add them all together, you get black, or the absence of color. I think that would work pretty well. But smarter people than I, wrote the rules here, so we'll stick with what they have. So if we think about what the strong force does, it's trying to get to a neutral charge here. Neutral charge is red plus green plus blue, okay? Or if you want to use, there are even anti-colors, anti-red plus anti-green plus anti-blue, add together to give us, no color. But in reality, one way to view this color charge is actually a three-dimensional vector, okay? Just like in the Cartesian coordinates, we have X, Y, and Z, okay? We can think about, arbitrarily a red axis, a green axis, and a blue axis. And this vector is constantly moving throughout this. So what we're trying to do here is have a red vector plus a green vector plus a blue vector get us to zero, okay? In classical physics, when we did classical mechanics, we added all the vectors together to get to equilibrium, where the net force would be zero. Think about this way. We want to have these color vectors add up to be zero. And that's the state that this likes to reach color equilibrium, if you will. So again, red plus green plus blue gives us no color, okay? And when we have the quarks, they have color. If we have the anti-quarks, we have what's known as anti-color. So red, what is the opposite of red? Well, going to subtractive colors. The opposite of red would be cyan. The opposite of green is magenta. The opposite of blue is yellow. Those would sort of be the anti-colors of my anti-quarks. And again, our protons and neutrons are held together because each quark has a total color of red plus green plus blue, which is no color or white. And then every anti-proton or neutron has an anti-red, anti-green, anti-blue. So when we have mesons, they will actually have a color charge of some, because they're a quark, anti-quark, they'll have a color charge and an anti-color charge. Okay? Oh, no, that's important for mesons to be held together. For a particle to be stable, the total color has to be zero. So a meson would have, say, a green and an anti-green, or a red and an anti-red, or a blue and an anti-blue. Okay? So again, let's use the analogy of the electric force. In the electric force, we have, positive negatives wanting to cancel each other out. So there's neutral charge, neutral electric charge. Here we're going to get neutral color charge. So there's our meson. Here's our color, and here's our anti-color. These two will constantly exchange the gluon, which will actually change your color. But at any point, this is oversimplified because it's saying all green, all anti-green. But, as they exchange gluons, this vector can rotate through space. It's just that the total vector, the total color charge at any moment has to be neutral for this. So pi meson is actually an anti-down and an up quark. And a pi minus would be a down and an anti-up quark bound together. Okay. So what happens in nature when you get greater complexity? We're going to, we'll talk about this later. The strong force is a special type of symmetry we call SU3. So as we get to more complicated symmetries, things get crazier and crazier. So gluons will have a color and an anti-color. So if I think of three colors, okay, three anti-colors, what are my possible combinations? Well, I can have red anti-red, red anti-green, red anti-blue, green anti-red, green anti-green. You get the idea, green anti-blue, or I can have my blue and my anti-color. Okay? So right off the bat, we think, okay, gluons. I can have 9 gluons. That'll work. But the reality is, and again, not wanting to go into too much detail, that the exchange of these 3 gluons does not change the color charge. So we actually don't have, in most models, we don't have the gluon where it's red anti-red, blue anti-blue, green anti-green, which would be a neutral color charge anyway. We actually have 2 linear combinations to replace those. So there are actually 8 types of gluons. Well, this just becomes a more and more fun game than we had before. So let's take the pi meson. Let's say that this anti-down quark and this up quark have respectively anti-green and green color charge. So that'll give it a 0 color charge. Well, this is not a static system. It's constantly evolving. They're constantly exchanging gluons to hold themselves together. So let's say they exchanged a blue anti-green gluon. Okay, we can look at this, one of 2 ways. It either went from the anti-down quark to the up quark, or the up quark gave off it in the other direction. So what is that going to do? It's going to change the anti-green color to anti-blue because it's giving off a blue to conserve blue color charge. If I give off blue, I've got to get rid of, I've got to gain anti-blue. If I'm giving off the anti-green, I've got to get rid of the anti-green on the left side. So that changes the anti-green to blue, anti-blue, and it changes the quark from green to blue. So as you can see here, right here, they have green, anti-green, okay, color charge. They exchange a gluon, and now they're blue, anti-blue, and certainly later on they can be red, anti-red, or some linear combination of the two as the exchange is going on. So that's sort of the dynamics that goes on here. But again, take this with a grain of salt. This is a model of what's actually happening. But it's nice because it does predict some of the futures that we have. Okay. I've got to give her credit. There's a physicist out there, Sabine, who has an excellent channel on particle physics and cosmology. And she brought up once that this is a really incorrect way of viewing the exchange of gluons between three quarks in a proton or a neutron, a hadron. And the more proper way is to sort of represent it this way, that everything is interacting simultaneously. This type of interaction wouldn't be allowed. But we really think about the three quarks being stuck together through sort of these almost like flux tubes of gluons between them. So that's a more realistic view of what's going on. But again, these are all models. So some models are better than other models. This, as we'll see, makes more sense when we talk about trying to remove one individual quark. Okay, let's do that. Let's say we want to pull quark off. Certainly, there could be enough energy to take that up quark and just send it flying. All right? Can't we recreate some of the early conditions where quarks were free? Okay, let's try to do that. What happens when I start pulling on this up quark? One way of thinking about these gluons is like springs. As you pull on springs, what happens? The restoring force becomes greater and greater. Now, maybe rubber bands are a better way of thinking about this. If I pull too much on a rubber band, what happens? It eventually snaps. And that's what's going to happen here. Quark confinement is something that is absolute. We can't free the quarks, because as we try to free the quark, I'm increasing my potential energy on this quark. Again, I've done work on it. I've hit it with a lot of energy. I've done work on it. It now has a lot of kinetic energy. And what happens is that kinetic energy is turned into potential energy. Well, the potential energy equals mc squared. Instead of keep stretching this gluon out, or this flux of gluons, would it make sense that I could turn some of this into a whole new particle-antiparticle pair? You see what happened here? I was putting so much energy into this, could we call it a bond? Yeah, almost a bond to the other two quarks, that I exceeded the amount of energy I need to create a new quark-antiquark pair, and boom, what's taking place here? I guess this is a proton. My proton is still there after the interaction, but all that energy went into creating a new particle, and this particle was a meson. This is a pi naught particle. Okay, so if you try to pull the quarks apart, they're like, nope. We come in threes or pairs. In this case, I created a pair, a particle-antiparticle pair, which is a whole new one. So I come in smashing these nuclei into one another, these nucleons into one another, and boom, I'm suddenly creating a whole new, stream of particles. And this happens, in particle accelerators. We smash protons together, and perhaps we have quark to quark collisions that take place, and all of a sudden I have these huge jets of new particles that are being created as a result. So that's the strong force. You hit an atom right? Hard enough, and you'll knock off an electron. And because our electromagnetic force goes by the inverse square of the distance, it's just like, okay, that's fine. You've overcome the negative potential energy by which that electron was bound, and therefore the electron can just go off in space. That doesn't work with a strong force, okay? The potential energy just increases with distance. And thus, what happens is we create new particles as a result. And again, this is a very superficial view of QCD, quantum chromodynamics. Everything here is conceptual. We haven't gone into anything very, very deep here. But, one thing to understand is, as these gluons are created, there's actually gluons will actually reconnect on themselves through other virtual gluons, and they just become stronger and stronger as we try to stretch them out, and this eventually creates this particle jet, if you will, new particle antiparticles coming into existence. And again, as long as we keep all of our expected values conserved, we're okay. Do we conserve energy? Yes, as long as we hit it hard enough, equals mc squared, I can produce new mass. Do we conserve baryon number? Yeah, I mean, I started with a baryon, I ended with a baryon. Mesons have 0 baryon number. Do I conserve, my number of up quarks? Yep. Here's 1, here's 1, here's anti-1, here's -1, here's 1, here's -1, here's 1. Everything here is conserved. I'm good. I can conserve spin. It's all conserved here. Now, there are cases which we create very exotic particles. And we're going to talk about 3 of them. 2 of them are shown here. But the third, we don't have experimental evidence with, so I'll sort of hold that to the end of our discussion. This is really neat. I said at the beginning, we have quarks in 3s, which are baryons. We have quarks in 2, which are mesons. But you can actually have 4 quark particles we call tetraquarks, tetra meaning 4, and 5 quark particles we call pentaquarks. Could there be even more massive condensations? I guess there could be. These are very unstable, very energetic particles, but we have observed the formation of these particles. So here of course is the tetraquark, and we have experimental confirmation, so we do know that these form. And it's like a big meson. It's like a big meson on steroids. It's a quark antiquark pair with another quark antiquark pair, and it doesn't violate any of the rules that we came up with. Is your color charge neutral? Yes, because this would have a color charge, this would have the anti-color charge. This would have a color charge, this would have an anti-color charge. So that works, okay? Does it violate, any of our other, requirements? No. We can have spin, anti-spin, spin, anti-spin. We can basically form these. They're just, because we're talking about much more mass, we're talking about much more energy, they're just, very unstable and decay very quickly into other particles. I don't know much about the tetraquarks, but I could imagine that this could very easily just decay into 2 mesons. That would be, a very simple thing to do. Here is a pentaquark. Now, this is sort of a hybrid of a, baryon, like a proton and a neutron. Here we have a proton right here, but we also might have a quark antiquark inside here. Okay, and this is interesting because some models are saying that the three valence quarks is not completely correct, that there's actually a quark antiquark in there too for the proton and the neutron, but I don't know enough but to really go into that. But the pentaquark would be three regular run-of-the-mill quarks put together and an addition of a quark antiquark pair inside there. And again, we could imagine this would decay very quickly into a hadron, into a baryon plus a meson too. I don't know the decay sequence of this, but again, we have been able to create these. Last particle, and these are exotic. We don't see these in nature. They are good to sort of tell us about, QCD. They tell us about how QCD operates, forming these exotic particles, but they really don't have a role in nature that I'm aware of. There's also the prediction that gluons could actually create their own particle. Remember, gluons attached to gluons. One could imagine that we could have gluons sticking together, what they call, yes, they're very inventive with names here, a glue ball, which is a particle entirely made of gluons. But although we've seen some resonances that may indicate such a particle, concrete evidence doesn't exist for that. So that's QCD. Again, going into the main ideas here, we have the heavier particles, the baryons, which are three quarks, which are bound together by gluons and a sea of virtual quarks and antiquarks, and we have mesons, which are basically a quark antiquark pair, which again are bound together by gluons. And this is the zoo of particles, which we became aware of back in the 1960s, when our particle accelerators became energetic enough to produce these new particles. And that brings up a very important point. In terms of seeing on a smaller scale, you can see how more powerful accelerators are required to actually see finer and finer detail. Some have proposed that quarks are made out of fundamental particles. We haven't seen any evidence of that yet, which would convince anybody. But if we want to see the finer structure of matter, the finer structure of nature, we've got to go to higher and higher energy. So in many ways, particle accelerators are not only microscopes, but in many respects, time machines. And again, just summarizing in terms of the quarks, because this chapter was called Quarks, we have 6 quarks. Up and down are the ones which are at the lowest energy. So all the other quarks which existed early on have decayed down into these quarks. And these higher energy quarks are not seen today unless we throw enough energy into these collisions so that new particles can be created.